All right, welcome in everyone. Today we're going to go through the product and quotient rules for derivatives. Okay, and so looking at that, let me share my screen and we'll get going. All right, so right now I title here our product rule, quotient rule for derivatives. To recall some items that we're going to kind of look at today, use that we had our limit definition for our derivative that focus in. That if we have our function f of x, when we go take that derivative, f prime, it's going to be that limit as h goes to 0 of that difference quotient f of x plus h minus f of x all over h, right? Letting those points get closer and closer, find that slope of our tangent line, right? And so then we can get our derivative, right? And some of our previous differentiation rules, we had that if I was to take the derivative of that function, we can go through that limit work. Same thing as f prime. But what I wanted to get into is that if we do the sum or difference of two functions, that derivative, d dx, the derivative with respect to x, we can just take the sum or difference of those individual functions, right? That's the same thing as saying we're doing f prime of x minus g prime of x. So with the power rule, derivative of exponential, we can start to go through that work. And again, it's all kind of based on that limit. The fact that we can separate terms in that limit allows us to separate those derivatives, okay? But the rules for products, right, multiplications of functions, and quotients, right, basically the division of functions, are a little more complicated. Okay, push this up. And important here, we cannot just multiply or divide the derivatives of the single functions, right? That is, when I take that derivative of the product between two functions, that's not equal to just simply taking their derivatives and multiplying those together, right? This doesn't work, okay? So instead we need to go through a little bit more work, okay? And so what we're going to do is the following. So this is just the setup of those, and then we'll get into the business of actually taking our derivative of that product quotient, okay? And so here we use a kind of algebra trick to find these differentiation rules, right? These steps, these rules to get the derivative of the product, and the quotient. So let's start off with our product rule. Okay, so in this case, we're going to go through these steps in order to get the process here. All right, so this is the rule to find the derivative of the product of functions. All right, the product of two functions, or later on we can extend it to 2, 3, 4 functions that are multiplying together. We can formulate a pattern. Okay, and so what we're looking for, the derivative d dx of the product of two functions. What is that going to look like? Okay, so starting off, right, when all else fails, we go back to our definitions, our fundamental steps, and we can say that this is going to be the limit as h goes to 0 of, now what are we going to do? It's still a product. All we're going to do is replace that x with x plus h. So the same interior, same function going on, same action. But now instead of just having a single f of x or g of x, now we have that product going on, maintaining that operation. So there's that limit format, the limit definition for finding this derivative. Okay. So there's exactly a pair f of x plus h minus f of x all over h, g of x plus h times g of x over h. We can't separate those, right? It's not going to be where I can just multiply those two derivatives. We just talked about that, or stated that fact. So what we're going to do, we're going to use an algebra trick. Okay. So what we're going to see is the following. Here, we will add and subtract the same expression in our numerator to rewrite and we get terms to help manipulate, right, to rewrite the overall limit. And again, it's kind of awkwardly stated there. So let's look at this, okay? So from above, with the limit, my organization might be a little bit different than the textbook, okay? But let's use this term. So I'm going to add and subtract the same exact expression. Which one you put first or second, the subtraction, the addition, doesn't make a difference. I'm going to put the subtraction first, okay? But I'm going to put here f of x times g of x plus h. And I'm going to add that same thing. And I know I kind of ran that space here, but we will. I'm going to keep the f of x, g of x in there. There, I'm sorry for that kind of crowding. I'll write a little bit smaller in my next line. But these are the pieces. Adding, subtracting, the same exact expression, right? That's like when we do our equations, right? Plus 5 minus 5. 5 minus 5, right? Adding the same value to both sides. That completing the square technique. You may recall for some of our quadratic equations, adding, subtracting the same value, right? If I was to simplify this, those would go away, and I'm right back where we started. So let me write a little bit smaller then. Because here, what we're really trying to see for us is that with these two terms together, or this expression, okay, these both have that g of x plus h that I'm going to be able to factor out. Then from these two expressions, these both share the f of x. And it's still all over h. Right, so it's kind of like grouping those different pairs. So now, right, these share that g of x plus h. We have here f of x plus h minus f of x plus, and on this side, these share the f of x, and left over g of x plus h minus g of x, and those are both still all over h. Okay, so a little bit of factoring there. By incorporating those two terms, it gave me something to factor from these pairs we created, these groupings. So now we have this addition between those factorizations, those pieces, over a single monomial, a single denominator here. So now, again, some of our algebra, we can separate those components over this single denominator, okay? So there's my h denominator, the same denominator for both, okay? Mouse cursor. But up top still again, g of x plus h times the f of x plus h minus f of x. On this side, our f of x times the g of x plus h minus g of x. All right, so separating that addition to monomials. I'm going to do two things here. We're taking this limit of a sum, right, of these two components. So from our limit laws, I can separate that limit or that sum into those individual limits. I break apart the limit or separate that sum into these two limits. So rather than combine the steps, let me just make a single step, right? So separating here. And now for this side. Similar, okay? So now separating that sum into two separate rational expressions, two fractions, then separating that sum into their own individual limits. There we go. And now just a little bit of notation. Again, algebra reorganization. Inside here, that g of x plus h is like a term multiplying that subtraction, that difference. So we could separate that off, peel that off, if you like, kind of like a coefficient, and multiply the rational expression. You can keep that numerator in brackets if you wish, or now that it's on its own, we can drop it out. Similar with this f of x, break that off and multiply by that difference quotient. Okay. We can do one more step with that limit. The limit of a product is indeed the product to limit. So this is where that would break apart individually. Okay. It doesn't work for derivatives, but for the limits it works. But instead, let's just think about taking that limit. Okay. So now, again, this is all in hopes of finding this product rule, this rule for taking the derivative of the product two functions. So when I take the limit as h goes to 0, right? As h goes to 0, g of x plus 0, this piece, this becomes g of x, right? H goes to 0, it's just g of x times, and now this expression, if I'm taking a limit as h goes to 0, f of x plus h minus f of x, all over h, this is the derivative, f prime of x. So this limit simplifies, creates this expression, this product, original g of x function times the derivative of that f of x function. Then we're going to add our limit here, right? F of x, there's no h there at all anyway, so that's just f of x, the original first function. And now that g of x plus h minus g of x over h, there's our g prime of x. And there's our product rule. So when we take this derivative of the product, the multiplication of two functions, what are we going to get? We find, and I'm going to switch my order a little bit, derivative of the first function times the original second function. Then we're going to add the original first function times the derivative of the second. And which derivative you put first or second is up to you. The book might have it the other way, f g prime times f plus f prime times g, right? Different books go with different orders here. But that's the way I kind of see it, because when I see that product, I see them multiplying these two separate functions. Two functions that involve x. Okay. Derivative first, keep the second the same, plus first function times derivative second. We can alternate those pairs. Okay. And so for an example, right? And so once we start to get more functions that we can manage, start to bring in some of our trig functions, so on, we'll deal with square roots. That'll be interesting as well. Okay. We can start to deal with those and include them in our procedures for taking these derivatives. So for a quick example, let's differentiate. This problem here, let's say we have d dx of x cubed e to the x, right? So again, like maybe it's our y is equal to x cubed e to the x, and we're going to find that derivative, that y prime. So our action, we're taking the derivative of this function. And what we want to identify is that, okay, in this case, my first function, x cubed, that polynomial, and I'm multiplying that with, I have this product with the second function, e dx, that exponential. So in order to find the derivative of a product, remember it's going to be f prime times g plus f times g prime. There's our product rule. Keep that rule in mind. So in this case, identifying our f and g, our function that we're multiplying, f prime, derivative of x cubed, right? That power rule, 3x squared. The power comes down, 3x, drop the exponent by 1, subtract 1 from 3, 2, 3x squared, right? So there's our power rule. And for the exponential, the derivative exponential, nice and simple, it's just the same exact exponential. We'll see a more complicated version of that later in this chapter, later in this discussion, okay, of taking derivatives. But for now, when it's just e of x, it's the exact same e of x. So following this pattern then, for my derivative here, it's going to be equal to, right, the sum of the product of those kind of different organization of the original function and a derivative. So in this case, with our work, f prime, which was 3x squared, times g, e to the x, plus f, which was x cubed, times g prime, which is e to the x again. Right, so taking those components, putting it into that format. So lastly, my y prime, right, that derivative, of that product, x cubed e to the x, we're going to get here 3x squared e to the x plus x cubed e to the x. There's our derivative. There's our solution. I'm not going to worry about too much more algebra, right? Factoring out that e to the x we could do, factoring out an x squared. You can do it, but definitely not necessary. Okay. And there's some ways to do those steps factoring out, but not a requirement at this stage. I want to see those steps for taking that derivative. Okay. All right. And so then let's switch pages here for our quotient rule. The derivative of a fraction, a quotient, a rational function. Okay. We could go through that same discussion. It's going to be a lot of algebra going on here. We're going to have a complex rational expression to manage, but it's going to be similar in discussion about adding, subtracting the same quantity, the same expression in numerator. Okay. The book might have a little bit different way of explaining, but again, that work is in the background. Once we get through a process, we don't necessarily need to go through that each and every time. It's just, right, if we ever get lost and we want to recreate, it is going through that work. But of course, we can just kind of look up these differentiation rules. So going through that limit work, let's jump down to the result that the derivative for a quotient of two functions is quotient rule. It's going to be a quotient going to be a rational expression. In the numerator, we're going to have the derivative of the numerator, f prime at x, times the denominator function. Then a key point here is going to be minus, right? Quotients go subtractions. Our numerator function, f of x, times the derivative of the denominator. Right, so similar to the product rule, derivative of the first function, my numerator that is, times the second function, the denominator. But now with the quotient division, we're going to see subtraction. First function numerator f of x times second function's derivative, denominator derivative g prime. But it's going to be all over our original denominator, that function squared. Okay. And that's going to be our quotient rule. That formula that we're going to have to remember. Right? This is the part of memorization that comes in. Memorizing these differentiation rules. Okay. So for example, let's find the derivative of this function. Let's say we have k of x is equal to this quotient, 5e to the x over x to the fifth power. Okay. So again, exponential polynomial start with, once we get more functions included in our differentiation rules, we'll have a lot more interesting and exciting problems to deal with. But again, looking at the structure, if I want to find that derivative, right, k prime, the derivative of k of x, what is that going to be? Okay. So in this case, again, we have a quotient fraction. I can't simplify, I can't cancel anything. So right away, all right, my f of x, my numerator function, 5e to the x, the derivative here, f prime, that constant, that coefficient stays with us. The real function, e to the x, the e to the x is e to the x. Our denominator function, g of x, that polynomial of power, x to the fifth, is derivative 5x to the fourth, right? Doing that power rule. So then for our quotient rule here, when I take that derivative, or k prime of x, okay? Right, we're doing the derivative dx of, and let me put those quotient components in color here, 5e to the x over x to the fifth. So doing that derivative in the numerator, f prime. So that's 5e to the x times g, x to the fifth. I'll keep that one in black ink because there's no derivative there. Minus, that subtraction built in, f, the numerator, 5e to the x times g prime, the denominator derivative, 5x to the fourth. And that's all over our denominator squared. Okay. And so is the second power in that denominator. And now the bit of simplifying we can do. Right, that derivative k prime of x. Let's just think that here. 5e to the x times x to the fifth. Let me sneak the x to the fifth up front. 5x to the fifth e to the x minus 5 times 5, 25, x to the fourth, e to the x. And now x to the fifth squared, x to the fifth times x to the fifth. You multiply your exponents, x to the 10th there. And now in this one, I will probably do a little bit of simplifying. The fact that we can factor out that x to the fourth, right? We can factor out a 5 as well, but and an e to the x, but that's not necessarily going to get us too far ahead. It's not necessarily going to cancel with what's going on in that denominator, which is my real focus. Let this x to the fourth can cancel and drop this down to a 6, right? 4x is up top, 10x is down below, canceling those. And so in the end, I might leave it in this rational form, 5x e to the x minus 25 e to the x over x to the 6th power. And like I said, you might see in other instances, we'll factor out that 5 and e to the x term, but for now, I'll leave it in that format. But the real work is memorizing the formula for that quotient rule, taking the derivative of a quotient of a rational function, derivative of the numerator times the original denominator, minus numerator original times derivative of the denominator, all over that original denominator squared in our product rule from before. Okay, so I'll leave it at that for this discussion, is introducing those two, see these quick examples. We'll have plenty of time to practice more product and quotient rules as we see further functions.